everyone, I'm Yuki Sakamura from University of Tsukuba. I will talk about multiview stereo based on omnidirectional epipolar geometry. This research proposes a new concept of geometry for omnidirectional images. Proposed omnidirectional epipolar geometry can remove the distortion of the omnidirectional image by rotation of the curve on the omnidirectional image to the sphere's equator. And also, I propose multiview stereo for the omnidirectional image using this geometry. Proposed MVS can estimate the depth with uniformity of the spatial resolution on the all latitude and continuity of the edge of the omnidirectional image by using proposed geometry. An omnidirectional image has spherical projection surface that can capture the all directions, so it is useful for various computer vision technology. However, to describe the omnidirectional image, particular projection method is used, such as equirectangular projection. In those projections, although the spherical projection surface is described as 2D dimensional flat image, the image cannot be defined as 2D images. For example, the left image is perspective image and the right image is rectangular image in the same scene. The object in the perspective image is distorted due to strong distortion in the equirectangular image. The equirectangular image has a property of more significant distortion at higher latitude points. On a line at latitude 0, the equator, the omnidirectional image has the original spatial resolution. This research proposes a new concept for pixel neighborhood of omnidirectional image and a multiview stereo algorithm for omnidirectional images using the proposed method. The proposed method removes the distortion of the omnidirectional image by describing the neighborhood relationship of the pixels as a one-dimensional curve based on the spatial resolution at the equator. First, I explain geometrical relationship of two omnidirectional cameras. Assuming that all cameras' position and orientation are known, epipolar geometry can be calculated using a geometrical relationship between two cameras. Essential matrix is given from camera's relative position and orientation. The equirectangular image is one of the projection methods for representing omnidirectional images. In equirectangular image, the horizontal axis is longitude and the vertical axis is the latitude. A mapping from equirectangular coordinates to rectangular coordinates is given this equation. Therefore, the epipolar constraint for the equirectangular image is given as this equation. Using this constraint, when one point on the omnidirectional image is given, a constraint that the other point should be satisfied is determined. The normal vector of epipolar plane is given this equation. And the epipolar curve for the equirectangular image is given this equation from the epipolar constraint. Proposed methods do not rectify the pair of omnidirectional images, therefore a calculation of limitation of corresponding range is needed. A green line is a baseline. The corresponding point is not behind this line, and the corresponding point is not behind the purple line. Therefore, the corresponding point is limited on the red curve. The equirectangular image has a property of more significant distortion at higher altitude point. It is caused by the difference in pixel spatial resolution while projecting a spherical surface onto a cylindrical surface. This difference is considerable at high altitude and smaller at low altitude. The spatial resolution of the equator's omnidirectional image lying on latitude 0 matches the original sphere's spherical resolution. The epipolar curve is the one-dimensional line that is same as the equator on the sphere. Furthermore, an omnidirectional image has symmetry in every direction since it has a spherical projection surface. Therefore, the epipolar curve can be mapped onto the equator by rotation of the omnidirectional image. This process is our proposal method. By using this method, the distortion of the one-dimensional line on the omnidirectional image can be removed. Specifically, it is achieved by rotating to match the normal vector of epipolar plane with the pole of the omnidirectional image. I will introduce multi-view stereo for the omnidirectional image using proposal method. The formulation of MVS consists of a data term and a smoothing term. A data term is a pixel-wise matching, and smoothing term is an optimization based on continuity of pixels. For the data term, the matching with the local binary patterns of Hamming distance are used. The local binary pattern assigns 1 to the target pixel if target value is smaller than the neighbor pixel values, or assigns 0 to the target pixels if target value is larger than the neighbor pixel value. So local binary pattern generates some digit binary number. The Hamming distance is the number of the different digit between two binary numbers. The data term is defined as a Hamming distance. The local binary pattern and Hamming distance do not compare direct pixel value, so it is resistant to noise and it is also quick to calculate. The smoothing term optimizes overall image based on the continuity of pixels. Semi-global matching is used for the smoothing term. SGM aggregates data term costs from the sum directions and can minimize energy function. However, conventional SGM does not consider distortion and continuity of edges of omnidirectional images. The line on the equirectangular image is actually distorted on the omnidirectional image, so the aggregation lengths differ depending on the latitude. Therefore, we propose a new SGM for the omnidirectional images. The curves for SGM aggregation is mapped on the equator respectively, and the costs are aggregated on that line. The proposed SGM can aggregate costs with spatial resolution, which is the same as of the sphere surface using omnidirectional projection geometry. Furthermore, the proposal method keeps the continuity of the image's edge while aggregation. The smoothing term is defined as the proposed SGM. Finally, some post-processing are used to adjust the disparity, a median filter and the cross-bilateral filter. The cross-bilateral filter compares the target pixel with the neighborhood pixels using both of intensity and disparity. Based on the differences of them, cross-bilateral filter calculates the weight of the neighborhood pixels. Such filtering algorithm defines the neighborhood relationship as two-dimensional Markov random field. However, it is not used for omnidirectional image directly because the omnidirectional image has a non-uniform spatial resolution. By using proposed omnidirectional epipolar geometry, we describe the neighborhood relationship on this sphere from the combination of some one-dimensional MRFs. We first calculate the curves through the target pixel and neighborhood pixels. All curves are mapped onto the equator respectively, and we reconstruct the block. This shows the example of neighborhood of 3 times 3. In this case, there are 8 neighborhoods, so 8 calculation is required. However, actually, 4 projections are sufficient since the pixel pair located at the opposite position are on the same curve. By using this method, we adapt the filters to the omnidirectional image. We experiment to estimate depth map using proposal method. The purpose of this experiment is to show validity of proposal method by comparison with conventional rectification method. The rectification method rotates the equirectangular image to match baseline on the north pole zenith. As a result of this process, the epipolar line is vertical and it has same longitude as PB. The advantage of rectification is to reduce the calculation of epipolar geometry. However, after the rectification, the distortion of the equirectangular image has been remained. The calculation of the date term and the smoothing term were the same as the proposed method, local binary patterns, semi-global matching. I will introduce generated dataset. Public dataset for omnidirectional image are small scale. There are almost not comprehensive datasets that have omnidirectional image, dense depth map, and geometric information of cameras. Therefore, we generated virtual dataset and real dataset for the experiment. Blender, a 3D software generated dataset. This figure shows the generated equirectangular image and ground truth depth images. It is virtual dome surrounded, and there is no infinity depth such as the sky. The dense depth map was generated by rendering engine to calculate distance from camera center to the mesh. The baseline distance was 1 meter. This result estimates the omnidirectional depth using generated virtual dataset. The left images are equirectangular images, and these images are ground truth depth maps. These images are depth maps generated estimated by conventional method, and these images are depth maps estimated by proposal method. The depth images are visualized by linearly changing over hue. A nearest depth is blue and the farthest depth is red. And this table shows the quantitative result of the conventional rectification method and the proposal method. We have evaluated 3 kinds of regions: overall, high latitude, and low latitude pixels. Mean average absolute error was used for evaluation. The error of each pixel was weighted based on the spatial resolution at the equator, because the spatial resolution of the equirectangular image is smaller at higher latitude. The result shows that the proposed method is more accurate than the rectification method for all the latitude. Next, we experimented by using the real dataset. The real dataset was generated using BLK360. BLK360 captured omnidirectional images and point clouds. The sparse depth map was generated by aggregation of point clouds. The baseline distance was 1 meter. This is the result to estimate the omnidirectional depth using generated real dataset. The result shows that the proposed method is more accurate than the rectification method for all the latitude. This is all result of virtual and real dataset. The result shows that the proposed method is more accurate than the rectification method for all dataset and all latitude. In particular, the depth was more accurate in the edge of the image and near the zenith, since the proposed method calculates both the date term and the smoothing term considering the continuity at the equirectangular image edge. These images are the result of 3D reconstruction based on estimated depth map. These results show the proposed method has more smooth mesh in the edge of the image and near the zenith than conventional method. The error can be classified into 4 types: textureless, occlusion, epipolar, and sudden change of disparity. These problems are the limitation of multi-view stereo based on geometrical information. Therefore, it is necessary to use methods that do not rely on geometric information, such as peak removal, plane fitting, and matching using visual information. Also, the proposed omnidirectional projection geometry has some limitations. One is considerable time complexity, since the distortion of the omnidirectional image are different from each latitude. Each pixel should be mapped. Furthermore, conventional programmatic technique for the conventional perspective image cannot be used, since the pixel neighborhood relationship is different. An example of the problem is dynamic programming for SGM. SGM can reduce aggregation of costs using DPs, since the result of aggregation can be used for neighborhood pixels. However, proposed methods cannot use the same algorithm, since each aggregation line is slightly different from neighborhood pixels. Therefore, implementation is different from conventional SGM. This is conclusion. Thank you for listening.